Another thing that we want to be concerned of is actually about hypothetical process path. So what is actually hypothetical process path? Hypothetical process path is the way how we can use in order for us to calculate the internal enthalpy, internal energy and enthalpy changes associated with certain processes, such as, for example, like if let's say there is a change from solid to liquid or solid to gas, so we need to use this hypothetical process path. The hypothetical process path, it involves five important things. Okay. For example, like if let's say there is a change in pressure at constant temperature and state of aggregation, where for example, like there is a change of pressure, but there is no change of temperature, there is no change of phase. So that is, you must draw that in your hypothetical path. If let's say there is a change of temperature at constant pressure and there is no phase change, this is must also be included in your hypothetical path. And if let's say there is a phase changes, for example, like from liquid to gas at constant temperature and pressure, such as melting, vaporizing, sublimation, condensing, and so on. So this is also to be included in the hypothetical path. And there is a mixing of two liquids or dissolving of a gas. Okay. And then there are also chemical reaction at constant temperature and pressure. So these are the things that we supposed to include when we actually performing energy balance in our hypothetical process path. So hypothetical process path is when we are able, it allow us to calculate delta U and delta H for these five type of processes, and we can calculate this for any kind of process. So if we are able to calculate for these five type of processes, then you should be able to calculate for any quantities. And this is where actually we must construct a hypothetical process path so that um, it have a certain steps in order for us to calculate the total enthalpy change or total internal energy change. After that, then we can calculate delta H or delta U, and we have to add all the enthalpy changes for every step. So in order for us to calculate the change of enthalpy in totality. So for example, like I have given you an example of how to actually turn solid phenol. Okay, so you know that phenol at 25 degrees Celsius and pressure of 1 atmosphere to vapor at 300 degrees Celsius at 3 atm. Okay, so we need to know that how we can actually calculate the enthalpy changes of phenol at 25 degrees Celsius and 1 atm to 300 degrees Celsius at 3 atm. So again, this is you have to refer to certain values that you can get from the appendix table. So in order for us to calculate the enthalpy changes, looks simple. For example, like we want to minus the delta H vapor, delta H specific internal energy at specific enthalpy at 300 degrees Celsius and 3 atm minus the specific enthalpy of phenol, which is in solid form at 25 degrees Celsius and 1 atm. But it has certain procedures in order for us to reach the state. This is where actually hypothetical process path and the reference state play an important role in order for us to determine the changes of specific enthalpy, changes of the enthalpy itself. And we know that if let's say we refer to any kind of table, there is no specific values for the specific enthalpy, and this is where actually we have to draw the what we call that. Do we need to draw this hypothetical process path? So let's start first at you know that we have actually 25 degrees Celsius 1 atm solid. Okay, this is given in the previous section here, where actually we want to turn the solid phenol at 25 degree and pressure of 1 atm to vapor at 300 degree and 3 atm. So Let's assume that we take the reference state to be at 25 degrees Celsius, 1 atm solid. Okay, so that will be our reference state. Reference state we can choose at any point. For example, you can choose at 300 degrees Celsius, 3 atm vapor. You can choose actually at 42.5 degrees Celsius, 1 atm solid, for example. But we have to be realistic that it's easier to choose either the initial state of the process as our reference state. So because we want to actually change from 25 degrees Celsius, 1 atm and solid, to 300 degrees Celsius, 3 atm and vapor. So we may want to start to pick 25 degrees Celsius, 1 atm solid as our reference points, as the starting point where actually we want to calculate the enthalpy changes from here to the final state that we are interested at. So how do we get the properties of phenol? Right, properties of phenol, melting point and boiling point we can get from the table. So I'm going to show you how do we get this value. Now you remember that we are actually going to calculate the enthalpy change for phenol at 25 degrees Celsius, 1 atm in solid state, to 300 degrees Celsius in vapor form, okay, at 5 bar. So how do you get the values of certain values? So it allows us to actually to calculate the enthalpy changes from the initial state to the final state. So if we first of all, we have to know that there is no direct values we can measure, but we have to get certain properties, certain information. So we need to go to table B1. This is where actually we got selected physical property data. Okay, and if you go to phenol, so straight away let's go to phenol. So in this particular table, you were given the formula, and then you were given the molecular weight, you were given the specific gravity, okay, you were given the melting temperature, you were given the latent heat vaporization of the latent heat of melting, and then you were given the boiling temperature, you were given the latent heat of vaporization, and then you were given the critical temperature, critical pressure, as well as the latent heat of this is actually the heat of formation. Okay, heat of formation will use more in the energy balance for reactive system, and heat of combustion. Okay, this is given in this particular table. And for phenol, we are particularly interested to know what would be the boiling point as well as its melting point, because the melting point for phenol is actually the changes. This is where actually at the temperature where the change of state happen. For example, like from solid to liquid, so at 42.5 degree, and then we have the melting heat of melting, which is at 10.54 kilojoule per mole. Okay, so if you recall that this is given in terms of kilojoule per mole, it's not kilojoule per kilogram. Okay, and then you have another one which is the boiling temperature, which is at 181.4, and then you have the heat evaporization, which is not being given here, but we can determine later. Okay, and then so these are the important points that we are actually collecting: 42.5 degrees Celsius as well as 181.4, which would be the boiling temperature as well as the melting temperature.